Good evening, everyone. This is Shruti. I welcome you all on the 8th live session of this course, which is Ultrafast Laser Spectroscopy by NPTEL. And the course is taken by Professor Anindya Datta of IIT Bombay. I am one of the TAs of the course, and today we will be discussing our weekly assignment 7th. So, no one has joined yet. Let's wait for a few students to join and then we can start the discussion. So let's start now. We are discussing the weekly assignment 7th today. Um, I know the solution has already been released by NPTEL, and you guys can match your answers with that solution PDF. And if you have any doubt, you can ask. Today we are discussing the answers given in that PDF. So the first question asks about the range of wavelengths obtained from Alexandrite laser is 1040 to 2010 nanometer, 700 to 830 nanometer, 600 to 1000 nanometer, 450 to 750 nanometer. So let's see what an Alexandrite laser is. Here you can see here this image, it shows Alexandrite is a crystal. This is those crystals. I have kept this image here. It's a shiny greenish purple, nice looking crystal, and it has some orthorhombic crystal structure. Orthorhombic crystal. So Alexandrite lasers are chromium doped. The Alexandrite crystal is doped by chromium. These are solid state lasers. Based on the crystalline gain medium. So gain medium is these crystals, Alexandrite crystals. That's why it's written that based on crystalline gain medium, which is Alexandrite. Gain medium is Alexandrite itself. That's why the name is Alexandrite laser. And what is Alexandrite? It is, as I told, chromium doped, chromium 3 plus, and it is Al2BeO4. Aluminium beryllium oxide. So these crystals occur naturally on our earth, but for the lasers, these crystals are grown artificially. But material for lasers So for lasers, we grow these Alexandrite crystals in the monocrystalline form. In the monocrystalline form with good crystal quality. And how it is grown? It is grown using this CZ technique. Czochralski growth technique. So these crystals are grown using this Czochralski method, and this method is used in semiconductor industries, used to grow generally used to grow monocrystalline or single it is used to grow single crystalline silicon wafers. So in this technique, what we do, uh, I'll just tell a little bit about this. Here we will have a bath kind of thing, and and in this and in this the liquid form, the melt form of these maybe silicon or this alexandrite will be there here. This is the melt. Okay, and one single crystal, a small seed crystal which we call as seed crystal will be there. This is a seed crystal, and this seed crystal is tied with a rope or knot, and we dip it inside the melt. It is dipped inside the melt, and then it is slowly pulled up. So this outside there is this is kind of some furnace which keeps the material in the molten state. So when this with the seed crystal, when this whole thing is pulled up, it creates a form of like this. The crystals keep on forming, and the crystal structure will be same as the seed crystal. So when you will keep on pulling, with the pulling rate is very slow, and that is decided with depending upon the so many parameters like the cooling rate and everything. So here maybe your seed crystal was there initially. So when it is pulled up, many crystalline things keep on growing, and since it is being pulled up, I can draw it like this. So this is a drip which is being pulled up slowly, and it forms something like this. And from this is a cylindrical thing. Maybe this is alexandrite crystal. The whole thing, it will be very big, and then we can cut pieces out of it. So then we can cut pieces out of it as we want. So that is what the CZ technique is. It's simply called CZ Czochralski method. So it is used to grow silicon wafers in the semiconductor industries. For semiconductor applications. Now let's see how where will be the application of our alexandrite laser. So I'm discussing a little bit about this because it was not being discussed much in the course. So just little bit about this laser where they are used. So generally they are used in dermatology. They are used in dermatology like for hair removal. We do laser hair removal. There are so many techniques for laser remove hair removal now. So in those we use Alexandrite laser, or for removing tattoos, or for treating pigmentation, or treating the veins. Okay, so how this Alexandrite laser removes hair? So it's like when we shine this long pulses, the hair follicles or the our heads, it absorbs those radiation, and that heat which is generated, it damages the hair. So that's how it gets removed. So this Alexandrite laser has a application in the laser removal therapies. So that laser does not cause damage to the skin because while doing that treatment, we cool the skin so that the top layer of our skin, which is the epidermis, so that doesn't get damaged. So here the question asked was, what is the emission wavelength for this? What is the range of wavelength obtained from the Alexandrite laser? So now so the answer for this is 700 to 800 nanometer, 700 to 830 nanometer, as given. That is the option B or C. That's the option B. So answer to this is this. So this is the emission related to the this chromium, this thing, chromium, aluminium. So that's why the answer will be 700 to 830 nanometer. So let's discuss a little bit about the construction. Initially, what we will have for just, we need some pump to start the laser, and for pumping we do at 530 nanometer because the emission is in this range. This slide goes, here is the curved mirror. Here will be one focusing lens, and here we will keep the Alexandrite crystal and at magic angle. So this is the crystal. Here one more curved mirror. Then then to remove the chirping, we will have a prism pair. And here one mirror. This is for output. This is a slit. This is M1, M2. M3. This is alexandrite crystal. This is M4, and we have two prism pairs. One prism pairs, two prism M4, and this is also a mirror M5. So this is how the construction of an alexandrite laser looks like. So for alexandrite laser, the spectrum is narrow. Narrower than dye laser. But it has only one disadvantage, that is why I am writing whatever is going. So the disadvantage is like the it cannot go with less than one. It is always, it cannot go less than 175 femtoseconds. So this is all about alexandrite laser. The first question was only about the emission wavelength. The emission wavelength is 700 to 830 nanometer, and this thing comes due to the crystal structure, due to the constituents of the alexandrite crystal, that is chromium doped Al2BeO4. So that's how this emission is coming. Let's see the next question. Luminescent concentrators usually utilize chirped pulse amplification, regenerative amplification, saturable absorption, total internal reflection. So luminescent concentrators. What is a luminescent concentrator? So a luminescent concentrator So what's a luminescent concentrator is, I have written the definition. It's a device. It is used to collect the radiation. So mostly it is used for collecting our solar radiations and feed it to the solar cells, which is used to produce the electricity. It operates on the principle of collecting radiation over a large area. It collects the radiation over a large area, and the material which collects the which upon which those radiations are hit on, and they give fluorescence, and the fluorescence is directed to a very small area. So it's like collecting the energy from a large channel and then putting it to a small area. That's what the work of luminescent concentrators are. So concentrators, luminescent concentrators means it is concentrating the luminescence, like mostly fluorescence of that material in a small area. So will its diagram will be like this. So let me draw a so this the top part will be the material, for example. So this part is coated with the material, with no gaps. Okay, so we have the pump light or the solar radiation like this. Okay, here we have the length of the concentrator, this is the width, and this is the height. So here the molecules are there. Okay. Why it is going? I don't get this. Okay, that's enough. Okay, these many molecules are okay. So when we shine pump light on this, so it will absorb the pump light and it will give its own emission, and that emission will be in all the directions. So this emission will be there in all the directions. But here what is the catch here is that these surfaces are polished, and this surface is polished, and this is the output surface, not polished. Okay, so when the emission hits here, what happens is what we call total internal reflection. So it will go hit and it will come back, come back, come back. Everything gets collected. So what? How many? There will be many rays like this. So this will go like this. So in the end, everything comes out. Everything comes out from here. So all light will come out from here. So this is what a luminescent concentrator is. So we have pump light, which may be LED or solar radiation, and the material undergoes, this setup undergoes what we call is total internal reflection. Total internal reflection, TIR. So all the light gets captured in this cavity and it comes out from one end. So for this material which is acting as a luminescent concentrator, this fluorescent material, it should have a very high quantum efficiency. Maybe quantum efficiency should be almost 1. Quantum efficiency should be almost 1, because if it is not less than 1 or not 1, then what will happen, we will lose the amount of light which we are giving in. So it is not giving out the exact output as the input which we are supplying. So we need the quantum efficiency to be almost equal to 1. So this that's how the luminescent concentrator works. So here, to answer this question, The answer will be the luminescent concentrator you usually utilize. Chopped pulse amplification, no, there is no chopped pulse amplification thing here. Regenerative amplification, no. Saturable absorption, no. It is using total internal reflection. So this is the answer. Now, what is total internal reflection? To explain that, I have given this picture here. I think all of you know what a total internal reflection is. So we have an interface like a denser medium and a rarer medium. So when light travels from denser to the rarer medium, what happens we know is the refraction. So light gets refracted away from the normal. That's what is happening here, refraction. Refraction. This happens when there is some random angle theta 1, there will be refraction. But when this incidence is happening at this angle, which is called the critical angle, which is theta c, then the light will go along the normal. So this is the normal. Light will go in this direction, along the normal, and like along the interface it will travel. So this is the critical angle situation. But for total internal reflection, what we give, the angle of incidence, the theta I or the theta 1, it should be greater than the critical angle theta c. So when it is greater, then the light gets reflected back in the medium, back in the rarer medium. Reflection back to the, sorry, denser medium. So the light is reflected back in the same medium. It does not escape the medium. So this is the principle of total internal reflection. And this thing is calculated using Snell's law, which we all know, that is n1 sine theta 1 is equals to n2 sine theta 2. N1 is the refractive index of this, and theta 1 is this angle. N2 is refractive index of the second medium, the rarer medium. Theta 2 is the this reflection angle or the refracted angle. So this is called Snell's law. This law, I think we have all studied in class 10th or 12th physics courses. So to answer this question, the luminescent concentrator works on the principle of total internal reflection, and it forms a cavity. The luminescence of this compound, which is quoted here, it is trapped in this cavity, and due to total internal reflection it gets reflected from this end, which is the polished end, and it comes out from one end. And for all this to work perfectly well, the quantum efficiency of this material, the luminescent material, should be 1. Otherwise, we will lose some amount of energy if it is not 1. So what will happen? We are not getting exactly that much radiation coming out from that much fluorescence coming out from the molecule as much as we are pumping light into it. So that's why we need quantum efficiency equal to 1. So let's move to the next question. So question 2 is about non-linear amplified loop mirrors find use in Alexandrite laser, titanium sapphire laser, ultrafast fiber lasers, or dye lasers. So non-linear amplified loop mirror. Here I have given the picture. This is a non-linear loop mirror. What happens here is that so what happens here is the signal is launched at port 1 here. This is the port 1. It splits equally at the coupler. This is a coupler and it experiences a differential phase delay along the two propagation direction, along this direction and along this direction, owing to the asymmetrically located amplifier. This is an amplifier. Here the signal traveling this way gets amplified, but the signal traveling this way doesn't get amplified. And here when they join back, we get output like this. So amplified output. So these uh, nonlinear amplified loop mirrors, they are used in ultrafast fiber lasers. They are used in ultrafast fiber lasers. So let's see here the construction of that. This has been discussed in the course. I'm just discussing for the sake of revision. And now we are at the end of the course near about, and the exam will be there soon, next month around this time. And I think you guys have registered for the exam. WDM is today my pen is not working well. So this is the construction of the uh, fiber laser, ultrafast fiber laser. We have wavelength division. This also got erased. Better do this. a wavelength division multiplexer. Here, this is the fiber, some couplers, and here is the nonlinear amplifying mirror. So, the question asked was nonlinear amplified loop mirrors are used in, so it is used in ultrafast fiber lasers. We saw Alexandrite laser here. So here we saw Alexandrite laser. There is no use of those loop mirrors, and we have seen in earlier classes, we have seen the working of titanium sapphire laser and dye lasers. So in those cases, we don't use any nonlinear loop mirrors. So the only option left is ultrafast fiber lasers. Here we use the loop mirrors. Moving on to the next question. The next question is about the phase matching condition for second harmonic generation is about conversion of energy, momentum, polarization, direction of propagation. So first what is second harmonic generation, what is phase matching conditions, and let's start with what is nonlinear optics. So for ordinary light, it has a weak field. Weak field and it gives linear response. So linear response means the polarizability is directly proportional to square is directly proportional to the electric field, or else we can write is directly proportional to chi1 e, where the chi1 is it is the first order electric susceptibility. So it is in terms of physical quantity, we can say how much susceptible a substance is to electric field, how much it will allow the electric field to pass through it. So that may be the electric susceptibility. So for ordinary light, which is the weak light, not much intense, the polarization, the P is the polarization. Polarization is linearly related to the electric field. But for very intense light, for example, our laser lights, pulsed lasers high electric field, so no linear response. So the response with the electric field is not linear anymore. What it will become? P is not linear, so it will depend on the higher powers of electric field. First power, second power, third power, and so on. It will depend on the higher powers of electric field. So, and this part, this chi2, chi3, these are called second order linear susceptibility. This is second order non-linear susceptibility. This is third order non-linear susceptibility. Let me write one here. This will be second order this is the second order nonlinear susceptibility, and generally we have the relation that chi1 will be very greater than chi2 and chi3 and so on. So it depends on the value of the electric field. If E is very less, E square will be less, E cube will be lesser. So it depends on the electric field. If the electric field is very high, then only these terms will come into picture. Then only these terms will play a role in the expression of P. So that's why it doesn't show up in the ordinary light. But for laser lights, electric field is high because the laser is very intense, so that's why these terms appear. Now this is about the non-linearity of the optical phenomena. Now it is asked the question that second harmonic generation. So let's see what is second harmonic generation. Second harmonic generation, it's like two photon absorption process of the and two photons should be of same energy. So let me show over here. So if this is a substance which has these energy levels and in between there is some energy level. So when a substance is given energy, maybe for example nu, so it will, this is, I can, energies are 0, nu and 2 nu. So when it is given a energy, it is excited with an energy of nu, it will make a transition from here to here, nu. And again, it will absorb a second photon and immediately it will make a transition from here to here. So we are the excitation pulse we are not changing. The excitation pulse is nu itself. But immediately it is absorbing a second photon and going to a higher energy state which has an energy of 2 nu. And from there it will make a downward transition and the energy released will be of 2 nu. So this is what we call second harmonic generation. Second harmonic generation. This thing we had discussed a little bit during our discussion of femtosecond optical gating. So when two photons of 800 nanometer meet, it will give a single photon of 400 nanometer length. And I have discussed numericals regarding this, how the conversion is happening, because wavelength is not additive. it is the energy which is additive, so we have to take inverse of it and then add. So when we are exciting with 800 nanometer, this is 800, this is 800, this is 800, we will get a up converted second harmonic which is 400 nanometer. So this is what is called the second harmonic generation. Now let's see what happens, what the question is asking is about the phase matching condition. So what are the phase matching conditions? And those crystals which give such phenomena, they are called, or the substance, not only crystals, they are called non-linear crystals. Here we have that non-linear crystal, and here we will have two frequencies, one which is second harmonic and one which is the input. And here we will put a short pass filter which will allow that second harmonic. Sorry, this is the crystal will have some optical axis. We will discuss about the optical axis little later. This is the optical axis. So now the electric field E is given by omega. These omega 1 is the angular frequency of the incident light, r is the position vector, and the ko is the momentum vector. So this is the electric field. Then the polarizability, which is the second order polarization, because we are talking about non-linear phenomena, so we are considering the second order part. E naught square cos square now this term we can write as this part gives the second harmonic, and this one is the constant polarization. So for the second, now let's come to the phase matching conditions. So we have something called phase velocity. Phase velocity is given by omega by k, and now k depends upon the refractive index, which is dependent upon the frequency. For phase matching, for phase matching we have k3 omega 3 is equals to k1 omega 1 plus k2 omega 2. So the phase of those incident photons k1, k2 should match with that of the resultant second harmonic. That's what the phase matching condition says. So now K's are what? These are related to momentum vector. K's are related to momentum vector. So this is the phase matching condition is about the conservation of momentum. That is, so in second frequency, in some frequency generation or second harmonic generation, when two photons combine, so they have to combine in such a way that their momenta is conserved. So this is what about is the phase matching. Pen is writing on its own today. So what I'm saying is the momentum of some frequency should be equal to sum of momenta of combining photons. Correct? So this is the phase matching conditions. So let's go back to the question. So the question is the phase matching condition for second harmonic generation is about the conservation of momentum, which we discussed just now. So let's recap a bit here. Now for non-linear optics, what we should have, we need intense laser beams, because ordinary light do not have that much strong electric field, so that the response of the polarization to the field is linear. So for non-linearity, we need laser beams which are highly intense. So the polarization depends on the higher powers of electric field, and those higher powers have a coefficient which are called the non-linear susceptibility. For example, if it is the second term, we call it the second order non-linear susceptibility. For third and fourth term, so on, we will have third and fourth order susceptibilities. So now, one of the phenomena of nonlinear optics is called the second harmonic generation. Now, what is second harmonic generation? In second harmonic generation, we are doing frequency doubling. Means two photons of frequency, single frequency, adds up to give a photon with a double the frequency. So for example, we are doing 800 nanometer plus 800 nanometer, we should get a 400 nanometer photon as a result of second harmonic generation. So these methods are used to uh, like to like up conversion it is. So we are using smaller lower wavelength, low energy, to create higher energy. So in this way these methods are useful. So here I have shown the second harmonic generation process when it is absorbing a frequency nu going to some energy state, and then immediately it is absorbing a second photon of the same frequency nu, because our source is constant. So now we are getting when it is emitting a photon which has energy of 2 nu. So this is the frequency doubling. Now for this, we came to the conclusion that for this to happen, since the energy is conserved, nu plus nu is giving 2 nu, energy is conserved, but for the phase matching condition, for this process to happen, the momentum should also be conserved. So the momentum of the resulting photon, this is the K3 momentum vector of the resulting photon, should be equal to the sum of the momentas of the individual photon. That's what is written here, that the sum of momentum of the some frequency photon should be equal to sum of momenta of the combining photons. So this is the phase matching condition. Only then this process will happen. Okay. So let's move to the next question. The fifth question is intensity of the second harmonic light is given by, and these are the options. So for this, I will just simply give you the answer. I will not derive it, and it is related to the mode locking kind of equation. So the answer is the first one itself. That is I of 2 omega. That is the intensity of the second harmonic light is equals to effective susceptibilities, second order effective susceptibility square, L square. L is the coherence length, then sine delta K L by 2 . This is the initial intensity of the source, the excitation pump. So This is the intensity of the second harmonic light which will come out, like this light. This 2 nu which will come out will have a intensity which is given by this expression. So it's like if we intensity is directly proportional to this I naught, the initial laser, the pump laser will have, if it is very intense, the second harmonic will also be intense. But there are some limiting factors here, which is like the L, the coherence length. So we cannot increase I naught too much. And also we have this term. This term is similar to the term we saw in mode locking conditions. Chi effective square. For some crystal, chi effective is very less, so the intensity of second harmonic does not go much high. For high chi effective, there are some conditions that we don't, so we need high chi effective. The crystal should not have a center of symmetry, because if the crystal has center of symmetry, there is no second harmonic generation or no nonlinear response. So for this question, answer finishes up to here, that this is the intensity, this is the direct expression given. Here it is L cube, which is wrong. Here we don't have the sign part. Here, here this part is cube, which is wrong. So these answers are wrong, right? Let's move to the next one. The next question is, the refractive index depends on the angle of incidence for both ordinary ray and extraordinary ray, neither ordinary nor extraordinary ray, extraordinary but not ordinary ray, ordinary but not extraordinary ray. Let's see what is the dependence of refractive index on the angle. This phenomena is called birefringence. So this is a birefringent crystal. Birefringent crystal means it has two different velocities for ordinary ray and the extraordinary ray. So suppose this light goes like this and then comes out like this, and there will be one which goes straight, and the crystal will have some optical axis. Okay, so if this light is vertically polarized, and drawing vertical polarization like this, then there will be a light coming out vertically polarized, and this will be called ordinary ray or the O ray. So for ordinary ray, the polarization does not change. Vertically polarized light remains vertically polarized. And for E ray, it will change to horizontal polarization. The polarization will flip by 90 degree. So this is the E ray or extraordinary ray. Okay, so from here the conclusion is that refractive index of so refractive index of the ordinary ray does not change. So different rays will have different refractive index, but for ordinary ray the refractive index is same. It does not matter what is the angle of incidence. Even if we excite like this or like this or like this or anyhow, for ordinary ray will not experience any change of refractive index, and its polarization will be retained. But the refractive index, that is the refractive index of O ray, is independent of the angle of incidence. But refractive index of E ray depends on the angle of incidence. And it has a perpendicular polarization it has a perpendicular polarization to the incident ray. So as I told, if the incident ray, this is vertically polarized, I will write here, vertically polarized light, the E ray, the extraordinary ray, will be polarized perpendicular to the incident light. Perpendicular to vertical is horizontal, so this will be horizontally polarized now. And the polarization of O ray will not change, it will remain vertically polarized light. So the refractive index of the E ray is dependent on the angle, but not for the ordinary ray. So to answer this question, we will have refractive index depends on the angle of incidence for E ray, but not the O ray. So the answer is C. It depends on for the E ray, but not the O ray. These are wrong. So when the angle of incidence is equal to the axis of the crystal, the optical axis, the refractive index for the E ray and the O ray will be the same. So that's how we define the, what I told just now gives the definition of the optical axis, the direction in which if the incident ray propagates so what I told just now is that when when the angle of incidence is along this optical axis direction, like this, if we'll excite in this direction, then the ordinary ray and the extraordinary ray will experience the same refractive index. So for a crystal, the optical axis can be in any direction. So we find the optical axis like this, the refractive index of both the rays will be same in that direction. So we have answered this question. Let's move to the next one. The next question is about the conditions required for second harmonic generating crystal is or are photochromaticity, non-centrosymmetry, birefringence, and presence of multiple optic axes. So let's see what are the conditions required for a nonlinear optical crystal. So the first condition is it should have high second order susceptibilities, polarizabilities, high second order susceptibility, and for this the crystal should be non-centrosymmetric. So if the crystal is centrosymmetric, what will happen? The polarization uh, generated in one direction will get cancelled away by the other opposite direction. So there won't be any net polarizability of susceptibility. So that's why we demand that the crystal should have should be non-centrosymmetric, and then it should have high value of effective susceptibility, second order susceptibility. And when so that's the same thing for centrosymmetric crystals. For centrosymmetric crystal, this thing will be 0, because as I told, that polarization in one direction will get cancelled away by the opposite polarization in the other direction. So this is the first condition, and let's write the second one in the next slide. So from here, let's first answer the question and then discuss one by one. This is not the correct one. Centrosymmetry is correct, birefringence is correct, and presence of multiple optic axes is correct. So I told now about the birefringence and the phase matching. Birefringence means the E ray and the O ray will have different polarization, and they should have different. Their refractive index should be dependent on the angle of incidence. So now why this is required? I think you must remember that Sir had drawn some polar plots, like this is the refractive index for the ordinary ray omega. Because it does not depend on the angle of incidence, it will remain constant. And this is my z axis, optic axis. And then let's take another color. For for along the optic axis, the refractive index of E ray and O ray is the same, so it should touch here. But also the refractive index for the uh, E ray is smaller, and it is angle dependent, so it will form an ellipsoid here. And this is for extraordinary ray for the incident photon. Now after the sum frequency generation or second harmonic generation, we will get the 2 omega photon, which will have, suppose this is a circle, so this is for 2 omega ordinary ray. And it will have this is the red one is the extraordinary ray of the uh, sum frequency. So when the phase matching condition is given by when the refractive index of ordinary ray of the sum frequency is equal to the refractive index of the extraordinary ray of the incident photon. This is the phase matching condition for second harmonic generation. And how this comes? This comes from, you remember in earlier slides I had written the phase matching condition K3 omega 3 is equals to K1 omega 1 plus K2 omega 2. And we knew the phase velocity is equals to omega by K is equals to C by n omega. So we can write k is equals to n omega by c from this. So here we can write n3 omega 3 into omega 3 divided by c n1 omega 1 into omega 1 divided by c plus n2 omega 2. I'm writing as a function. Refractive index is a function of frequency because it is frequency dependent every time, divided by c. C will get cancelled away, so simply n3 omega 3. It is understood that it is a function, so I am not writing here. n1 omega 1 plus n2 omega 2. Okay. For now, for second harmonic generation, second harmonic will have omega 1 and omega 2 are equal, and omega 3 will be equal to 2 times of omega 1. That's what is the second harmonic. So we replace these things here, then we will get 2 omega 1 into n3 is equals to n1 2 times n1 omega 1. Okay, and these two will get cancelled away. Omega 1 will get cancelled away, so we are left with n1 should be equal to n3. That is, n1 is for omega 1, it should be equal to the refractive index of the some photon. This from here we got that equation. This is the phase matching condition for all the crystals which give the second harmonic generation. So at what points in this polar plot we see this condition is true? So at the points where the plots for n02 omega coincides with the plot for Ne of omega. So this is the blue one is of Ne of omega, and n0 of 2 omega is the green one. So at what points the blue and green coincides? So there here is 1, 2, 3, 4. So there are 4 points at which these so at these 4 points we at 4 point n02 omega and n refractive index of omega of extraordinary ray has same value. And these points are what? These points refer to angle because it's a polar plot. It's a polar plot, so it's some angle. It's some angle with respect to the optical axis. So let me draw. So this is the angle and this is the optic axis. This is the angle theta. So if we will keep the crystal at this angle, then only we will see the some second harmonic generation or the some frequency generation. So this is also one of the conditions for getting the second harmonic. So our question was about the presence of multiple optic axes. If there are many optical axes like this, then we will have many such angles and we can get second harmonic at so many angles. So it will be easier to tune the uh, to tune the angle. So if we have only one optic axis, then there are only one angle. This is the angle. Or in the reverse direction, it will be this angle. In the reverse direction, it will be this angle. So if there are many optical axes, we will have many angles to keep. So that's why the question, we can have this option also as correct. That is, the conditions required for second harmonic generating crystal is it should be non-centrosymmetric, so that we have high value of chi effective. It should have birefringence, so there are different refractive index for the E ray and the O ray, and presence of multiple optic axes, so that we can tune the crystal at different angles to get the second harmonic. Okay, so I hope the question is clear. So let's move to the next one, and this is the last question for this assignment 7. The question is, angle between polarizations of the fundamental and second harmonic beams is 0 degree, 22.5 degree, 45 degree and 90 degree. I think I discussed this question somewhere here in the birefringence, that angle between the polarization of the fundamental and the second harmonic. So if we have this non-linear crystal, this is a non-linear optical crystal, and we are giving this is 800 nanometer, for example, and after the for example, here is the generation, we will get a 400 beam also after second harmonic generation. Second harmonic, this is the second harmonic. This, and if, and we can separate this by keeping a filter over here. Now let's talk about the polarization. So if this is the incident pulse, incident 800 frequency, and if this is horizontally polarized, I'll show the horizontal polarization like this. If it is horizontally polarized, so then the second harmonic which will be formed out of it will have polarizations perpendicular to it. Why? Because it is a type 1 phase matching. So perpendicular to horizontal, it will be vertically polarized like this. Why? Because we are having here what is known as type 1 phase matching. Pump, signal, idler. Pump is E, signal is O, idler is also O. So in this type of phase matching, the polarization of the second harmonic will be perpendicular to the polarization of the fundamental or of the incident line. So the fundamental here is 800, which is horizontally polarized. So the second harmonic which we will get out of it will be 400. So to answer this question here, the answer will be angle between the polarizations of fundamental and second harmonic beam will be 90 degree. How this happens? This happens due to the nature of the type of phase matching, which is type 1 phase matching. The pump is the E, the signal and the idler is of OO type. That's why we get type 1 phase matching. That, and here lambda of the signal is equal to lambda of the idler. So if E is 0 degree polarized, O sorry, here O is 0 degree polarized, the fundamental if OA is 0 degree polarized, then E will be 90 degree polarized, perpendicular to the O, exactly perpendicular to the O. So this is called OOE type phase matching. Two beams of 0 degree polarization is going to give this is type 1 phase matching. This is type 1 phase matching. And because of this reason only, you remember in the FOG setup, the femtosecond optical gating setup, we keep the Barrett plate or at the Barrett plate not at the magic angle, but 90 minus the magic angle. So I don't have the setup here now, but the fundamental is here. It creates, it is this polarization. Suppose it is horizontally polarized, and here is the crystal. It gives, and here is some separation happens. We get this one here, and this one goes here, and then here is the Barrett plate. Is some mirror. Here will be the sample, and sample is giving green fluorescence, and then here is the retroreflector setup, and then it comes and merges with this one, and here one more nonlinear optical crystal is there. From there we get the sum frequency. So this is the FOG setup. So here the Barrett plate, this is not kept at magic angle, but 90 degree minus the magic angle, that is 54.7 or 57.4, sorry, or whatever. So it is 90 degree minus that magic angle. 90 degree minus the magic angle. Why? Because this is horizontally polarized. So the some frequency which is the blue light, it will be vertically polarized here. This will have a vertical polarization, but we need to cancel the anisotropy effect with respect to the fundamental, because the fundamental is going to meet with the fluorescence light and give the some frequency. So that's why we keep the periplate not at the theta angle, magic angle, but 90 minus theta, because this one got flipped by 90 degree. So the magic angle here is basically 90 minus theta. Okay. So I hope the questions are clear. This was the last question. And we have come to the end of our session today. Okay, so we have finished the discussion of assignment 7. And today was our 8th session. Next week, next Friday, we will be discussing the assignment 8, same time, 7 to 9 p.m. And yeah, I hope you are learning the course well.